everybody? Okay. So let me go slightly um, uh, slightly back and remind you. Yeah, it's recorded. Okay, and remind you what we have discussed last time. So basically, we are talking about we're considering integrability in conformal field theory. So, and I'm advocating the point of view that it's very similar. I mean, it's very similar to how we use integrability in spin chains and so on. So we have an R matrix, and the definition of the R matrix is probably go even back over here. So the definition of R matrix is this one. So I have two bosonic fields, phi I and phi j, which themselves they're just the bosonic field they generated Heisenberg algebra, but they commute among themselves. So I just have taken two copies of Heisenberg algebra, and we have a product of two. I call them Lax operators, which intertwines Heisenberg representation of the Heisenberg algebra and differential operators. And Q is a parameter here, which parameterizes the central charge. So R matrix is just, I mean, for me, the definition of R matrix is just this formula. Okay, it's probably different from what you might be familiar with, and I mean, like standard definitions of R matrices. Sometimes it's given by explicit formula. Sometimes it is defined through the, universal R matrix and taking representation of it. For me, I will simplify things. Just think that it is defined by this very special RTT relation. So this is RTT relation, and it defines R matrix. It defines R matrix up to a total scale, up to total factor, which is not, of course, cannot be fixed here because you can multiply both sides by scalar function. Okay, now I skip all these things and just remind that, in fact, our matrix essentially depends only on difference of these two bosonic fields. You can easily see that relation, RTT relation, it just implies that R matrix commutes with the center of mass. So d phi I plus d phi j divided by 2 commutes with R matrix. I mean, physically it just means that R matrix is an operator depends only on J, which is by definition J is this 1/2 of the difference. And then the defining relation is just this. It's not that convenient. It is more convenient to work in terms of modes. So as usual, I expanded. It's not written here, but as usual, I expand. Let's say I work on a circle. I expand J in terms of Fourier modes, denoted by A with subindex n. And then I have this set of infinite set of defining relations. Okay, so I have two types of Virasoro generators, L plus minus. They only differ by this plus minus sign here. And this difference, I mean, both of them generate the Virasoro algebra with the same central charge, parameterized by Q. More precisely, central charge is 1 plus 6Q squared. And this sign does not matter because central charge depends on Q squared. So the sign in front of Q doesn't matter. So both of them generate isomorphic Virasoro algebras, and what operator R does is just intertwines between these two. It's basically given by this formula. If everything, I mean the highest weight parameter and the central charge are arbitrary, I'm assuming this, then this set of relations is enough to fix all the matrix elements up to total scale, which, for example, you can fix by saying that R acts on a vacuum state by just 1, for example, for simplicity, and then you easily produce all the states. Here is an example. Once you know that R produces L minus from L minus 1 plus produces L minus 1 minus, then you just substitute this expansion in terms of bosons, act on the highest weight, And then you really end up with this formula. So Rx on Heisenberg first excited states by this formula. But going deeper into the model, of course, the action will be more complicated, but you can easily predict the denominators of this. First of all, it is clear just by from the definition that this is a rational function with spectral parameter. Yeah, I have to warn that here, the spectral parameter plays the role of the highest weight. Highest weight. Probably better to say it other way around. Highest weight plays the role of the spectral parameter. So you can easily predict the denominators of these rational functions. Of course, zeros, you cannot predict them, but denominators appear then. The corresponding Virasoro model becomes degenerate, but I will not use it. So you know all the denominators, but numerators are more complicated. Okay, let's move on. So as I explained, I just repeated very quickly that having defined the R matrix, I can define, I will call it Yangian, probably in generic Yangian story, it is, I mean, for SL2, for example, it is what is known as generalized Yangian or Yangian of GLN rather than SLN. So this algebra is just, for me, it will be just the algebra of whose generators are L encoded by the monodromy matrix L, and it has an infinite set of quadratic relations written decoded by this formula, RTT. Usually it's known as RTT, a presentation of the Yangian. Okay, so each L here is some operator which acts in some quantum space, and it's labeled, it has two indices, like Bryan-Cat indices. Both of them are partitions. So generic element of this algebra is labeled by two partitions, lambda and mu, as shown here. And of course, as usual, we can do the usual thing. It's like a kind of Gauss decomposition, but here's an infinite dimensional version of it. But nevertheless, to do the Gauss decomposition, mainly we define three basic currents, actually four basic currents, H, E, F, and psi. They just defined as shown here, which is just their definition. Very similar. The first line here is very similar to SL2. Basically, probably up to switching E and F. I think that I'm kind of using non-standard thing, and for me, E will create states other than F. Fortunately, for some reasons that happened. And also psi is more complicated. Also, we expect the following expansion at large values of the spectral parameters written here. So the coefficients at the infinity are my modes of the currents, and they basically constitute the Yangian. Well, some auxiliary thing. In principle, there are infinitely many currents, and for some reasons, in order to enumerate the currents, it is rather convenient to use plane partitions. I'll not explain it either, but there are higher currents corresponding to next level. The fundamental current E corresponded to one box. Now we have like three additional currents corresponding to a plane partition consisting of two boxes. There are three of them, and they defined as I show here. It's just explaining the definitions, and then sorry, I have to have said about my notation. It's not here. Yeah, okay, I will say it in words. So then you can, just using the RTT relations, you can compute the relations of these currents. I already said that, so epsilons here are Nekrasov notations. They just replace my parameter Q in conformal field theory, which is usually substituted by b plus b inverse is the standard thing in CFT. And so epsilon 1, epsilon 2, and epsilon 3, it's more or the same as b, 1 over b, and minus b inverse, so that the sum of epsilons is 0. This is just parameters. So we have these commutation relations with the commutation functions, which are kind of, I think, new compared to the standard Yangian, because in standard Yangian you would have linear function of the spectral parameter. Here the functions are cubic. As you see here, there's the zeros located exactly at plus minus epsilon. And also you have set relations, which are cubic up to what I call local terms. So let me also briefly remind, because it will be important later, that these relations are not just, they're not that simple, meaning that you just permute currents. They're so-called local terms. Local terms depend only on one spectral parameter rather than two. I mean, meaning that the corresponding currents are inserted at one point, and they are local. Sometimes they call boundary, because once you expand this relation in terms of modes, expand everything at both infinities, u and v expand an infinity, then it is clear that each of the blue terms contribute to the commutation relations only to a very small part of it, only when one index is fixed and another goes from 1 to infinity. That's why they do not contribute to the most of the relations. That's why they call boundary. Okay, now I do very standard thing. My goal is to is the following. Once we have RTT algebra, Young-Baxter algebra, Yangian, whatever, there is a Bethe ansatz. There is an infinite set of commuting integrals of motion, and it should be some way to describe its eigenstates and eigenfunctions and eigenvectors. Okay, and so that's basically my goal. There is an ambitious goal to compute matrix elements of the local operators between the Bethe states, but this is still undone at the moment, so it's still in progress. So first of all, first ingredient of this construction is so-called zero-twist integrable system. So probably I'll explain later, remind you later why it is zero-twist, but just, sorry, I scroll back a bit, show that my generators H and psi form a commutative subalgebra. You can think of it as the Cartan subalgebra, and let's us diagonalize it first as a preparatory step. So let's suppose we have some representation of this algebra. I will study a very specific one in a sense, and so I want to diagonalize H in this representation. I call it zero-twist integrable system. So the construction is very simple, but I think we use it's very common to what is usually done in this type of problems, but I think we use some a bit non-standard approach. That's why I will explain it in a few details. Okay. So let's see. So suppose I have an eigenvector. I'm not even specifying now which representation I have, just the idea. Suppose I have an eigenvector lambda, large lambda, which is an eigenvector with some eigenvalue h. So it's denoted by the same letter. I mean, practically, you might try to create new state by applying E to the state, but of course it doesn't work, because the commutational relations of H and E, they're not just permuted as an ordinary SL2. There is this local term here. That's why in general acting, so E acting on lambda does not create the new eigenstate. But suppose that this action on lambda has some singularity, basically a pole at some value of V, which depends on lambda. Let's denote this point X. Then the second term of this permutation relation, it does not depend, it cannot have this pole. If the left-hand side does have a pole at some value x, then the right-hand side, only in the right-hand side, only the first term might have a pole. Because the second one is a local term which does not depend on v, on my variable, in which in which my expression develops in singularity. That's why if this is the case, then the residue of this pole, I'll call it lambda tilde, is a new eigenstate. Moreover, you can easily compute the eigenvalue just from this commutation relation. That's very simple idea. And of course, so this is how you basically proceed. You start from, now you have to pick a representation to complete this task. So suppose you started from the highest weight. It is by definition will be the eigenstate of H, and then you apply E, and each time you not just apply E, but you look for the singularity, and kind of at each step you have kind of bunch of singularities. You pick one of them, and that's how you create the eigenstates. And you proceed, because this is infinite dimensional algebra, you proceed infinitely many times. You might be worrying that your currents E, they do not commute. You remember that they form some algebra, including the local terms, and that means that probably so taking the singularity, it might depend on the order in which you take these singularities, which state you obtain. But in fact, it is not. And well, I will not explain it into more details, but in fact, how to say, you can have an image that your states, in a simple situation, your states are labeled by partitions, but not by Young tableaus. So different Young tableaus, meaning Young tableau is how you fill your Young diagram with the numbers. I mean the standard Young tableau. And different tableaus will correspond to the same eigenstate, because you can, because of what is written here, basically you can permute different e's in your eigenstate without, basically it will affect only on the total factor, and it will be actually the same state. So what is written here. Now specified to a particular representation, I'm taking a very special case where my space, I will call it quant, no matter how I call it. So my space in which I act is a tensor product of Fock spaces with the highest weights x1, xn. So basically, I know how the basis in this space looks like. It's labeled by tuple. Sorry, by tuple of n partitions, lambda 1 with the upper index 1, etc. n. And the only ingredient I need is how my Cartan subalgebra acts on the highest weight. So my highest weight, by definition, h on it x just 1, and psi x with this rational function. It can be computed. Let me skip this part. So once I know this, I can immediately construct the eigenstate. I call it lambda vector. Vector means tuple n partitions of n. Large n is some fixed number, the level. And you can construct this state from a vacuum state applying generators E. And so these contours means that at each step you will have a simple pole, and these simple poles are located in what I call contents of the Young diagram or partition. Okay, so there is a box in the partition. It has two coordinates, I and j, and there is a corner of this partition which is labeled by k. K runs from 1 to n, so you fill n partitions with these contents, and this is written here. Scrolling all over all tuples of partition, you will generate all the eigenstates. Okay, this is very simple. Very simple thing. So we constructed zero twist integrable system for this particular type of representation. If you wish another representation, you pick another. For different representations, you will have different actions of psi that will basically produce different types of representations also, but I will stick on this simplest case of tensor product of n Fock spaces. This is analog of spin chain of length n with inhomogeneities x1, etc., xn. All right, now what I'm doing, all right, so I have a, in principle, I have more. Yeah, sorry, I should also mention that this zero twist integrable system, last time there was a question, so it corresponds in a simple situation, simplest meaning length one, only one Fock model. It corresponds to Benjamin Ono type integrable system, zero twist. If you have length n, it's kind of matrix version of it. Okay, I think discovered by Lebedev and Radl. But a quantum version of Benjamin Ono, of course. But I would, but there is more general integrable system called intermediate lock wave. It depends on the twist parameter, which is not zero. I'll call the twist parameter Q. So I'm just taking the twisted transfer matrix. The twist goes through the total L naught. The L naught in the auxiliary in the space in which I'm taking the trace. You can twist with the L naught operator, and then you expand, as usual, take the transfer matrix, expand it at some point here at infinity, and you obtain, let me call them, semi-local, quasi-local integrals of motion. They local from the point of view of this imaginary spin chain, but from the point of view of my field theory, they're not quite local, but semi-local. I explained that they contain this operator D, which is not exactly local. All right, so in principle, it is. So my goal is to diagonalize this transfer matrix, and but instead I will diagonalize the very special this transfer matrix evaluated at the special point. I will take. Sorry, it's not written here. I'll take the tensor product of n Fock models. Now the highest weights are called u rather than x, and I evaluate the value of the transfer matrix at the first, for example, highest weight or inhomogeneity, and the result of the evaluation is nothing but this q to the power L naught product of R matrices. This is very simple. Okay. Now I come to the construction of the beta vectors. Let me call them off-shell beta vectors. In order to do so, I have my quantum space, and the inhomogeneities of base I called by U, and I also need some auxiliary space, which is tensor product of large capital N Fock spaces with the parameters x1 and xn. So this n, it's like what we would call the number of magnons in ordinary spin chain. Here is the level of my representation. As you know, in conformal field theory, all representations are there is a degree operator, which is just like holomorphic part of the energy operator. So everything starts with some state which has a specified conformal dimension, and then you grow with you create states, and they all arrange with respect to L naught, and so its eigenvalues are the eigenvalues of this L naught is some delta, which is highest weight plus an integer amount. This is exactly that integer amount n, which enters this formula. Okay, and then another ingredient, I'll need a special state in the auxiliary state. I call it chi of x. It's a very special state. It's kind of, I filled homogeneously. I put one box in each vacancy, okay? And so meaning that I just have I acted by the product of n large n creation operators and have taken the residues just at the corner of each Young diagram. Very simple thing. And another ingredient which I need is this. You can easily compute this type of scalar product of chi and this product of n. Sorry, it should be large n here of n annihilation operators. You can easily compute it. It's some symmetrization of this rational function just from commutation relations. So these are basic ingredients which I need now. Now I formulate what is, I think, known in the literature as a Tarasov and Varchenko construction of shell beta vectors. So instead of writing the formula for it, I will draw a picture. So this is the picture. B of x. What is it? It's a state. It's some special state in my quantum space. My quantum space is vertical one. It is, I mean, and the parameters are u. And it is obtained by the product of R matrices sandwiched between the vacuum, the bra vacuum state in the auxiliary state and the chi state taken as a ket state, okay? So everything here for me acts like operators in this picture act from right to the left and from top to the bottom, okay? So this is, you see, it's this product of R matrices. Each cross here is our R matrix. I have taken this product and sandwiched, act by this product on a vacuum state in quantum space and sandwiched it between two special states in auxiliary space. If you imagine SL2, then chi is very simple. It's just spin up, spin up, spin up. And this is nothing else but the product of BBBBB operators. Is usual thing in algebraic beta ansatz. But this is the generalization of it. Okay, this now I take let's call the weight function. What is the weight function? I just take the write this wave function in terms of components and just act I project this state b of x on some on a state in my quantum space. It depends on choice of base. I just pick the basis, very standard one, just monomial basis in this Hilbert space. Okay, so this is the definition. Omega lambda is this scalar product by definition. So it's just a function now, and I'm trying to convince you how to describe this function in terms of some contour integral. So here's an answer. Let me explain it. What is written here? So I'm saying that this weight function first, it is rather explicit but very complicated function in fact. So there's some rational explicit function f times the matrix element of the following form. It's not, you cannot see all of it, but you can guess the pattern. So you have like h times product of f's, and then again h products of s, and it is repeated n times, and then at the very right side you have the chi state. So it's a product between vacuum and the chi state of such n types, n factors starting with h and then fff, okay? Why it is so? You can see it from this picture. Once I have taken some component of here, then I change the point of view and think of it as a matrix elements of a product of L operators, matrix elements of the L Lux operators acting in the auxiliary space. Okay, now I explain why it is so. So, right, where such kind of formula might come from. So let me briefly explain. So I want to explain this. Any matrix element basically between any two states in the auxiliary space, you can express it in terms of certain add operators applied to the H operator. it is almost obvious that this is the case. So, but let me still explain where it comes from. So from the definition, so let me define. Oh, sorry, I paused. Yeah. So let me define the U1 current, UN. Just by definition, it's an action. It's a matrix elements of my Lux operator between ket vacua and some excited. Oh, I'm sorry. Oh, I'm sorry about that. It's a fire alarm in the building. I'll go outside.
Выгоняют?
Выгоняют просто всех сразу.
Что такое? Прям в эфире.
Ну, в прямом эфире вот России. Вы что хотели? Свободный суда, что ли?
Давай не будем это самое. Психически заглянуть. В какой стати там нужно?
Что им такое у них? С пониманием надо относиться, у них такой режим.
Женщина какая-то говорила там.
Ну, это администратор.
Дроны.
Ну, это академия.
А ну-ка спросить, что ли, где нехорошо.
А ладно, не издевайтесь.
Что-то... Я был там, но это коридоры, что-то я не помню.
В смысле? Он так и выглядит. Вот это вот здание, которое...
Был.
А может, вы еще в Красной Будке были, кстати?
Нет, в Красной Будке не был.
В таком здании круглом, да?
Yeah, I'm very sorry. It's a fire alarm drill. So it's not a real fire, but we kind of. Sorry, can you hear me? Is it
Yes,
okay?
да.
Works?
Hear you. But what was the point?
Sorry. Can you still hear?
What? Alyosha, we hear you. So everything is okay. Continue.
We can hear you when you are not moving. So if you stop here, if you stop somewhere, we can hear you.
I'm sorry. Can you hear me? I turn back.
Yeah, we can hear you.
Yeah. I'm so.
Yeah, so, but no screen.
Yeah. It's a fire alarm drill. It's not a fire, but everybody had to leave the building. So.
Okay, now we can see the screen also.
Yeah. Thank you. So just a sec. I'll go to full screen. Yeah, what I just said. Yeah. Let's find the mode of U1 current. Then the commutation relations of the R matrix imply that the following R matrix, which is basically is this thing. It's a product of R matrices, so it's just one side times n sides R matrix. Then it satisfies the following computational relations. Basically, commute with the total total U1 current. Probably remember I have told that it's called the center of mass. It commutes with the center of mass. It's the same for ordinary Yangian. And then just from this, taking the matrix element of this with some excited state, you will recurrence. So adding a line with n boxes to a partition is the same as commuting with the mode of the U1 current. And just from here, you obtain this relation. Some starting from H, which is L nothing comma nothing, you just apply F naught or F1. It's enough to apply these two things to generate any partition here. So just remember that the matrix, the matrix operator between some excited state, some partition, and vacuum state is just this add type of thing. Now, okay. Now, another point. You have I claim that these matrix elements can be represented as a following integral, where all f operators are put to the right. Why it is so? With some function f which depends only on lambda. Why it is so? So the problem is that, as I explained, L is some adjoint action of the modes of my current f. But since it's adjoint, some of them are placed to the left. I have to have a way to move them to the right. I have this way because I have the commutation relations. So first of all, Fn placed to the left of H is I pick some mode at infinity, right? So I integrate, I multiply by xi to the n and integrate around infinity to pick this mode. Then under the integral, I know how to commute f to the left. I can do it. But I have two terms. One which I like, and another which I don't like because it's, I mean, if I will keep all these local terms in such a computation, it will become a mess very soon because I have many adjoint actions, and that's why formula will not be very convenient. But you can notice that this total expression, it doesn't have a pole. And let's say xi equals to u minus epsilon 3. The sum of these two terms doesn't have this pole. That's why I can extend the integration around infinity and include this additional pole here. It doesn't affect this relation. But what it does, basically, you can see that the local term, which depends on xi very explicitly. I mean, the current itself does not depend on xi, only this rational factor. That the total integral around both of these singularities is 0 because you can shrink it like to 0 where it doesn't have a pole at all. So under the integral, the following relation holds. So under the integral, you can permute h and f, provided that you have surrounded, so your contour is such that you surrounded all the singularities. How to say, all I mean infinity and apparent singularity, which comes from the commutation relations. So once you surrounded all of them, it's free just to permute without taking care of a local term. This is how any adjoint action is basically can be reduced to this, with the price of computing some function f, which is very explicit, and you compute it for any lambda. Then another ingredient, of course, you know how to compute. I already said it. You know how to compute this intersection between my chi state and f states. This is just symmetrization of this rational function s, and from this you can just compute. You can compute the weight function very explicitly. It is complicated expression, but you can wrote a algebra program in Wolfram Mathematica, and in principle compute for any given tuple of partition, you can compute omega very explicitly. It's some function, which is very explicit but complicated. But at the moment, I don't need it. I just explained how to compute it, okay? Okay, so after all, we end up with some weight function, which depends on what? It depends on my highest weight parameters, which are fixed sorry, so let me scroll back to the beta vector. Beta vector, or its weight function, which is just its projection on the monomial states. It depends on my parameters of my highest weights, which are fixed. I don't move them, and also on auxiliary parameters x's, which I vary. And the way I vary them, I have to find a locus of x's such that this state is the eigenstates of my transfer matrix. So I constructed what is called off-shell. Off-shell means that x's are not fixed, and they like move around, and I find discretized locus of x such that this state becomes an eigenstate. So how to do it? Let's proceed to this construction. Okay, the 20 minutes. So I have this very simple formula. So instead of acting by the transfer matrix of this on this off-shell beta state, I will act by its value at the u1. So this like intertwining operator is the value of the transfer matrix at the value at u equals to u1. What it does is very simple. Then it acts on my off-shell beta state. It just takes the first to the left space and just drags it all over others, and then it becomes first from the right, and also multiplies it by q to the L naught. So the action is very simple, but this is not the eigen. Of course, it's not an eigenstate because it changes it. It just takes the first to the left and just drags it to the right. Very simple, right? It just follows from this construction from the Yang-Baxter equation. You can easily prove this relation. In each step, you use Yang-Baxter relation, and then the R matrix, which is here, it goes all of the. You can go like drag it up, and here it acts on vacua, and this action is just one. This action is just one. That's why it just disappears. So it disappears everywhere. It's very a very simple thing, right? So this relation here, in terms of the weight function on projecting basically this relation on the monomial basis, means the following thing: that the matrix elements of this T1 operator is the matrix element where you have, first of all, q to the power, which is the length of my first partition attached to the first space, times this matrix elements there lambda L with the index lambda 1 is permuted to the right. So what I have to do, basically, I have to find a way how to drag it to the left, and then I'm done. If I will able to do that, then I just find a condition that these two states are proportional, right? So this is what I demand here. If we require that my off-shell beta state, which I constructed, is an eigenstate of the operator T1, we just demand this. So I have. So this is for any choice of partitions lambda 1, lambda 2, etc., lambda n, the following should hold. So the matrix element, let's read this relation from right to left. The original matrix element, which is sorry, I have to escape from here because kind of yeah, just one sec.
На улице прям, да, да и небо вижу, слушай.
Yeah, you see on the right you have the weight function and the order of partitions lambda 1, lambda n. On the left we have reacted by the long rotation, muted lambda to the right.
Алеша, плохо слышно, слушай. Ты подходи к зданию хоть немножко, да. Что-то совсем на улице вышел. Слушай, туман, что ли?
Сейчас, одну секунду.
Что там туман, что ли, Алеша?
Не туман, тут это... Шар.
Понял, что он говорит. Что-то он запутался. Алеша?
Одну секунду, я переключу на мобильный интернет. Это заработает сейчас. Еще ты...
Спокойно. Что делает?
Он переходит из сколько на свой мобильный.
А, свой мобильный, да.
Идет на стадии интернета. А она будет
Что?
сказать,
Да ну,
Mobile internet, it should work fine. Yeah, tell me if you can hear me. And... Right? Is it okay?
Слышно сейчас, да.
Okay, thanks. So now, first of all, I have to do full screen.
Что-то.
Okay, so
Continue, Алеша, давай.
yeah. Just a second, I just done something and I don't see. Yeah, I continue. So what I have to do? Let's see. I have to find x's such that this relation holds. First of all, I equate. I can compute the eigenvalue. I take lambda 1 to be empty, because if it's empty, it makes just nothing. So the action of L nothing comma nothing is just my operator which acts not acts on the left side and on the right hand side. Equating this, I can. So T1 I know. And then what I do, very simple. I have I know how to compute H with F. I know it up to local terms, but I'm claiming that my integral is very special. It surrounds all singularities, meaning including infinity, where I pick my the modes of my currents, and also including the apparent singularities which come then I commute currents among themselves. I claim that under such contour integral, you don't have to worry about the local terms. That's why you can permute things pretending they just permuted without local terms, only be local. If you do so, then, if you do so, you just compare two sides of this relation, okay? I'm sorry. Yeah. So let's see, for example, if for example, I have to commute H of U1 to the left. Then I do it. It commutes with all F, which it meets on the road. Then I commute all Fs from the last group, basically from the first group to the left as well. It meets all F and H on the road. All commutation relations I know. They are like Fs commute with itself up to local terms. It's the commutation function is a ratio. It's a rational function which has 3 zeros and 3 poles. Exactly this one. The zeros are at epsilons, and the poles are at minus epsilons. Once you commute everything and you equate two integrals, both integrals will differ only by the function f. One function to the left and another to the right. They will differ by the commutation factor. This factor is depends on your integration variables. But once you know that the integral is computed. Sorry, I had to say it here. Let me return to that point. So, sorry, it should be here, right? So my my weight function, I can compute everything, and what remains is some contour integral of a known function omega with some kernel, which is also known. Moreover, my contour integrals go around all singularities, apparent singularities which appear from commutation relations and also from the infinity. But there are singularities which are not surrounded. These are basically the points axis, my to be the Bethe roots. Okay, so I surrounded everything except axis. So that's why by just Cauchy theorem, my integral basically localizes to axis. Okay, and this is how, sorry, I had to say this here. So this is how I explicitly obtain the weight function. So important point here is that no matter how my, no matter what kind of things I integrate, my, sorry, no matter which function f, large f, is in under my integral, if I surrounded all its singularities, and I'm doing this by definition, then the integral localizes to the x, variables x, which will be my Bethe roots. And from here it should be clear. These two integrals are
Ivan,
by the function.
it's not something deformity your hair or something voice.
It forms my voice. Yeah, that's not me. It's not. Yeah, I'm sorry. Sorry for that. Yeah.
Yeah, now it's better.
Now it's better.
Yes.
Yeah. So I assume that I explained that the integral localizes to the locus. Sorry, I'm almost switching. So the contour integral picks some contribution of the Bethe roots. So these two integrands, they differ by a factor. And once you evaluate it at the, no matter which pole you take, it will be just this. It will be proportional to the product Q, basically to the product of such products. Okay. It depends on how many F's you computed to the left. Just trust me that once you computed everything and try to equate the left-hand side to the right-hand side, and once you have chosen the particular pole contribution, then both hand sides I agree, provided that the ansatz which is called. I think this is clear. So this is kind of it's very similar to how it usually goes when we cancel the unwanted poles in the Bethe ansatz equation, but kind of the new ingredient, more general compared to the ordinary Bethe ansatz technique, is that we diagonalize unoperated. So, you know, I think I will not go into details, but let me just say, I had also all slides for boundary Bethe ansatz equations and also for more general algebras. But yeah, let me say a few words about more general algebras. So what we considered here, what kind of problem did we solve basically? What we studied? We studied the integrable systems, quoted spin chains, obtained from Yangian of GL1 hat. GL1 hat is the same as Heisenberg algebra. And we studied spin chains such that basically there are more representations than I just studied. I considered only one. So this way we obtained integrable system of a closed Toda type, which I started with. Closed, meaning affine AN Toda, but twisted. We have this twist parameter Q. It's almost affine, except that it appears to be affine, then Q goes to 1. Okay, how you can generalize this? First of all, the simple generalization, you can consider more general representation of the affine Yangian. What kind of integrable system you will obtain? In fact, a lot. For example, one of them, and I'm just telling this for those who knows. One of them would correspond to what is known as complex Sinch-Gordon integrable system, or you can obtain more general thing known as sorry, I forgot the name of this system. Now, what kind of integrable system you would have if instead of GL1 you consider generic GLN? Again, it depends on the type of representation in quantum space you have. One kind of representation which is similar to this will produce you new integrable system, which is I think unknown at the moment. It will be published soon in my paper with my students. So basically, you can imagine this integrable system as Toda, as closed Toda chain, such that in each what to say particle is not just one bosonic field, but instead it's a GLN Verzumina model of arbitrary level. So you have like chain of GLN Toda, GLN Verzumina model in each particle. Generally Toda chain, and there is kind of Toda-like exponential interaction between them. So this is a very general thing. Another point of generalization is to consider study a level 1 because algebra. In this case, you will obtain a certain metric for and even more. So all this business I'm saying now only about closed spin chains, but considering boundary spin chains, you will obtain more integrable systems and more conformal film theory. So this is, I think, I'm come to the end. So this is very general framework of studying integrable systems in conformal film theory, and I have touched only very small, but it kind of I think it gives you a little glimpse of how general construction works. And yeah, much.
So you finished.
I finished. Yeah, please come to your questions.
Thank you. Thank you very much.
Hopefully, I will see you.
So questions, Sergey.
There's no camera, no.
No camera? No, we saw you. It's okay.
But you see me, but I
Your
can
voice
can
is
see you.
format. We see
Yeah,
you.
sorry. Yeah, thanks.
Voice was more
Fine.
complicated.
I want to see you, but yeah, please do the questions. Sorry.
Yeah. Yes.
Now I see. Yeah, let's see. I'm trying to focus.
Yeah. Okay, no question. Okay, thank you very much.
Thank you.
Yeah, see you
Please
in
see
Yerevan. Yes.
some of you somewhere in the world. Very
Yeah,
soon.
in Yerevan.
Yeah. You graduate person in Yerevan. Okay, thanks a lot.